Welcome, Tadip.
Shandeep, good afternoon.
Welcome.
Good afternoon, Surajit.
Welcome, Vishnuda. Welcome, sir. Welcome, Professor Mukhopadhyay.
Welcome. Thank you. How's everybody?
Fine, sir. Doing well.
Yeah, am I audible? Audible?
Hello, sir. अच्छा, okay, 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 okay. Well, wait, sir. Welcome, Dr. Shah.
Is it okay?
Hello. Shantanu sir told me to wait a little bit, just a few minutes.
Is there any false sound? Any false?
Shantanu sir, welcome.
Thank you.
Actually, we are just waiting for Shantanu boss sir. Welcome, sir.
Sorry, I'm very late. Surajit, welcome.
Thank you, sir.
Okay. Okay, I think, Shanti, we should not waste time and let us
Right,
start.
sir. Right,
Yeah.
right,
It's
sir.
better. Yeah.
So, at the outset, sir, I would like to express my sincere gratitude and thanks to the council members of the Structural Geology and Tectonic Studies Group India for gracing this online platform. Now, I'd like to welcome Dr. Surajit Misra, Assistant Professor, Department of Geology, Gauhati University, to deliver the monthly lecture of this month, organized under the aegis of Structural Geology and Tectonic Studies Group India, in association with Department of Earth Sciences, IISER, Bhopal. Before I hand over the stage to Dr. Misra, I would like to provide a brief introduction about today's speaker, mainly for our young students and other listeners across India who have joined also through our YouTube channel. Dr. Misra earned his BSc from University of Bardhaman and subsequently MSc from Calcutta University and MTech and PhD in 2014 from IIT Kharagpur under the able mentorship of Professor Saibal Gupta. Subsequently, he joined as a project scientist in BGRL Karad under Ministry of Earth Sciences before moving to Guwahati University in Assam. He has also authored more than 15 research articles in reputed journals, and he is also handling government and funding projects worth more than 1 crore rupees. Presently, he is working on the petrology, microstructure, and geochemistry eh, and rock strength measurement and crustal stresses within basement granitoids underlying the Deccan basalt, and also on the structural and tectonic evolutionary investigation of the Shillong Plateau, Northeast India. So now I request Dr. Surajit Misra to present his talk on the mineralogy and structures below Deccan Traps, evidences from scientific drilling in the Koyna seismogenic zone. Welcome, Dr. Misra.
Yeah. Thank you, Sandeep. Am I audible? Am I audible? Okay.
Yes,
Okay.
you are.
Thank you, Sandeep, and thank you, sir, for giving me this opportunity. Here, good afternoon to all of you. Here, now I am going to talk about mineralogy and structures below Deccan Traps, evidences from scientific drilling in the Koyna seismogenic zone, India. Before delivering this presentation, I must acknowledge my previous organization, that is BGRL, under the Ministry of Earth Sciences. Without their support, without any facilitating this core samples and other facilities, it was not possible for me to do this type of research activities. I am getting benefited from all sides from the BGRL till now. Now, the main problem is related with the ongoing seismicity in and around the Koyna reservoir. Before going to that, there is a line. This line we can consider as a reference line that is basically representing the escarpment of Western Ghats, Western Ghats escarpment, or the elevation change from mean sea level to the higher elevation of about 1,000 meters
Surajit,
from the mean.
just sorry to interrupt you.
Yeah, yeah,
Have you changed your slides yet or
yeah, yeah,
no?
yeah. I have changed it.
But it is not changing in your presentation.
Okay.
We are still on the title slide.
Is it visible?
Yeah. Now it
I
is
think
visible.
full screen mode, some problems are happening.
Mm, okay, let's try once again. You go to the full screen mode only.
Yeah.
If everything goes all right, then we can continue. Yeah.
Okay, fine. Here, the area is basically representing the Koyna Reservoir area. It is the Koyna Reservoir, and here it is the Warner Reservoir. And this line is basically representing the Western Ghats escarpment, which basically separates the western part, which is nearby the mean sea level, and this one is approximately 1,000 meters high from the mean sea level. Now, this Koyna Reservoir is basically filled up in 1962. After that, around 1967, this area was triggered by a major earthquake that was around 6.3 magnitude Richter scale. Followed by this earthquake, another reservoir is there, Warner Reservoir. Again, it was activated, and there was a major
Surajita, you are not audible. Hello,
Hello.
Surajita.
Am I audible?
Now we can. Yeah.
Hello.
Surajita, you have to share your presentation once again. Yeah. Otherwise.
Is it coming? Hello.
Yeah.
Am I audible?
Yeah. Now it's fine.
Hello. Hello.
Oh, it's fine now. Audible.
Here.
You can go to the first slide.
But I'm not audible. Hello.
You can go to the first
Yeah,
slide.
we can hear you, Surajita. We can hear you now.
Hello.
Yeah, we can hear you now.
Yeah. But I'm not getting sound. I don't
You
know
are
why.
audible, Surajita.
I'm getting some problems.
Shandip, I think you can call him over mobile.
Yeah.
So and tell him.
Hello.
We can.
Am I audible?
Yes, you
Yeah,
are
Surajita, you
audible.
are audible.
Hello.
Please go ahead.
You are audible, but we can't see your first slide.
Just insert it here, back side, if there is any. হ্যালো
হ্যাঁ, তুমি হেডফোন ছাড়া কথা বলো।
ওইটাই করছি।
খুলে দাও, হেডফোন খুলে দাও। হেডফোন খুলে দাও।
Jain Sahab, namaskar. You are not audible. I think you are
You are
muted.
muted.
স্যার প্লিজ কেটে দিন, মানে এটাতে সমস্যা হচ্ছে, এটাতে নেটওয়ার্ক কানেক্ট আছে।
Surajit, we can hear you perfectly.
Yes, sir. That is the problem. Network
No. We can hear you. We can
Okay,
hear
okay.
you. Please go ahead.
Yes, sir. Yes, I'm doing it. Yes, sir. Yes, sir.
Please
Surajita,
upload your
please,
slide.
share your slide. Yeah.
Share your slide.
Is it starting now or I have missed something? Shantanu?
Yes?
Is it starting now or I have missed something? I have
No,
joined
no,
late.
no. It was started, but now there is some
Sir,
problem.
sir,
Yes,
can
yes,
you
it's
hear?
fine. Yeah,
Okay,
yeah,
okay.
yeah. Yes, okay.
Yeah,
Just
thank you, sir.
make a
Thank you,
full
sir.
make a full screen and go ahead.
The full screen is getting problem. That's why I'm facing.
It's okay from just like this. You go ahead.
Yes, yes,
No
sir.
issue.
Thank you, sir.
No
Thank
issue.
you, sir.
No issue.
Yeah. Yeah. Sorry for disturbance. Here, basically, this area is representing the Koyna Varna area. It is approximately 10 by 20 square kilometer area in the Western Ghats. Here, if you see the magnitudes of earthquakes from 2 to 3 magnitude earthquakes, maximum earthquakes are around 2 to 3 magnitude earthquakes, where white and yellow dots are maximum in this domain. Now, if we want to correlate with the magnitudes of the earthquakes and amount of energy released during these earthquakes, they are basically, you can convert in terms of the TNT, where the amount of TNT generally used to generate this type of earthquake equivalent with the large quarry mine blast in any region. Now, basically, I'll go the superficial mapping of this Dhonichawadi fault or fissure zone in the Koyna Varna area. This is the first map I have prepared in 2017. And here the fissures, basically, I have measured from this area. It is representing a north-northeast, south-southwest trend within the study area. And this linear alignment is basically representing the Koyna fissure zone that was generated just after 1967 earthquake. Now, these are the superficial field photographs of the fissure zone, and these are the first field photographs was published in 2017 after the 1967 earthquake. Around 1968, there was a map by the GSI. They have prepared a map, but at the time there was no field photographs of these fissure zones. Now, after getting borehole samples from these areas, basically these are representing different boreholes. Before this, I must introduce that all the boreholes are near vertical in orientation, and it in all the boreholes penetrates up to 1.5 kilometer depth, and entirely it transits the basalt, Deccan basalt, and penetrates into the basement gneissic rocks. Here, it is very clear that overlying basements are underlain by these cratonic rocks, which has a different geochronological barrier. Now, these are the clear evidences where Deccan basalt is directly overlying on the basement rocks. Now, basically, this study is related with the structures and mineralogy of the basement rocks. Therefore, my interest will be on the basement rocks. These photographs are basically representing the drill codes from the basement rocks that is underlying below the Deccan basalt. Here you can see the 4 samples with proper strong gneiss that is representing the interlayerings of quartzo-feldspathic and mafic banding layers, and all these boreholes are representing the down deep direction, that is the near vertical orientation. Now, within these boreholes, the fractures, those are natural fractures, they are following the pre-existing fabrics orientation in most cases. At places, you may found some sort of near vertical fractures, those displaced the pre-existing features. Now, photomicrographs of these basement rocks, it is basically representing the typical gneissosity within the cratonic gneisses. Here, the interlayerings of felsic-mafic layers are very common, where at places quartz grains are highly stressed, and kinked and recrystallized muscovites are very common following the sheared fabrics. So within these basement rocks, at places it is expected some sort of strong intense shear fabrics are there. Those are basically defined by the recrystallized muscovite and preferred orientations of chloride following the sheared fabrics. Now, these are all the pre-existing fabrics present within the basement niches. Now, after getting the core samples, there are thousands of core samples are preserved in BGRL. Basically, from there, I have logged this entire KBH 1, 5, 6, 7 borehole samples. Here, 1, 6, and 7, these borehole samples, lithologs are representing western part of the escarpment, where KBH 5 is representing eastern part of the escarpment. All the boreholes, they have penetrated up to approximately 1.5 kilometer depth level. Now from here, just here you can see the length of these boxes, or this length dimension we have considered around 1 meter. So with respect to the recovered core samples, with respect to this 1 meter length, we have classified into 4 categories. Category A, Category B, Category C, and D. Apart from RQD, here we have classified this nomenclature as a SQD, sample quality designation, for our purposes. Now here, the core samples, recovered core samples, those are lesser than the 25 centimeter in length, means the length 5 centimeter to 24 meter, we have termed it as category C, and lower than the 5 centimeter in length, generally we called it as category D. Basically, C and D core samples, here you can see that these are representing the fractured zone or shattered zones within the basement rocks. So most of the C and D zones within these boreholes, they are basically representing the fractured zone or fault zone or ruptured zone within the basement that is underlying below the Deccan basalt. Now, one disadvantage of these core samples are none of them are oriented. There is no northeast, there is no indicators or indications of the north position of these core samples. Only one thing we have, most of these boreholes are near vertical in orientation. So with respect to these boreholes, we have measured the angular orientation of these fractures and fabrics with respect to the vertical borehole axis. Here, KBH 1, 5, 6, 7, in all cases, fractures are naturally following the fabric's orientation. But in case of KBH 6, if you see, there are several near vertical fractures. In case of KBH 7, some near horizontal fractures are also there. Now, it is expected fractures will follow the natural fabrics, but somewhere they are cross-cutting or parallel in different orientations. Now here, KBH 1 and 7, KBH 1 is nearby the Koyna reservoir, KBH 6 is nearby the Warner reservoir, and KBH 7 is basically locating nearby the recent pilot hole borehole that is up to 3014 meter depth. Now, after that, the borehole samples or core samples we have recovered. Here, if you see, the core samples here are representing basically from different boreholes, different depth levels. They are showing highly fractured zones with proper slicken lines on slicken sides. Most of these fractured zones, they have reddish in color, and these slicken lines with prominent slicken sides. These samples are from KBH 1. These 4 samples are from KBH 5. These four samples are from KBH 6, and these 3 are 7. Now here, in case of KBH 5, if you see these surfaces, and these are the zones where core samples are highly fractured and shattered. On the surfaces of this fractured surface, if you can see, these are near vertical, down deep slicken lines. At places in KBH 6, on this surface, there is a very thin blackish layer of this pseudotachylite. On the surface of this pseudotachylite, there are strong lineations. These are basically slicken lines. Similarly, in another case also, slicken lines are there. Now, these are all related with the brittle deformation. I am not saying these are related with the ongoing deformation, but these are the evidences of the brittle deformations. Now here, in other cases, in other samples, here, these samples are basically from the basement rocks. Here, if you see, there is a near vertical. All the boreholes are near vertical. This arrow is representing down dip direction. All the boreholes are near vertical, and this one is the near vertical fractured or fault zone. This fault or surface or fractured surface, we can say it as a master fault, and right angle with this master fault, there is near horizontal fracture. Those are mostly tensile. So during friction on this surface, the generated material, basically pseudotachelite, that is injected inside the adjacent tensile cracks. But in other cases, these three samples are representing the fault breccia or pulverized zone. Here, if you see the clasps of the basement gneisses, that is, they are aligned and long axis, they are indicating a particular direction of shearing or movement within this fault zone. But if you see the color of these samples, they are highly reddish in color, but none of them are representing any potash feldspar or any other minerals. Basically, these are iron, highly ferruginized. Okay, here you can see the class of felsic material is embedded within this fine-grained gauze material, but that is entirely compact due to the ferruginous precipitation or cementation. Now here, within the same type of material, if you see, there are very thin, fine hair cracks are there, along which some white or grayish material is there injected along the fractures. These are basically either siliceous or calcareous. If you put some sort of ACL, it will give you the effervescence. So here, most of these fractiated samples, here, this zone is representing the pulverized zone or grinding zone within the basement. They are compact and they recovered their somehow their rock strength because of this secondary material or ferruginized precipitations or cementations within this pulverized zone. Now here, another sample here from the same basement rocks. This sample, if you put some water and just press it by your hand, it will be crushed. Okay. Now, in another case, it is a layer, it is a vein of calcites. It is a calcareous material. Another, this one is the silicon site, where this surface is coated by a secondary material. It may be siliceous or calcareous. Okay. Now, in another case, the material from the friction surfaces I have collected, these are basically typically representing the silicon lines on the silicon sides. If you see this surface, it is looking like a very fresh. Point is, all the friction surface, they are very fresh without any type of alterations. But they have secondary precipitations or coatings on this friction surface. Here, this material, it is a grinded or pulverized material within the fault zone where silicon lines are prominent. If you add some water within this, it will behave like a mud or it will crush by using your hand pressure. Now, these are the physical properties of the fault zones materials, but somewhere the angular orientations of these fractures matters within these faulted or fractured zones. Now, this sample, it is representing a near vertical fault surface, but coated by a secondary material. This material is basically calcareous. If you put some sort of ACL, it will give you the effervescence. Now, here, these are near horizontal fractures. All these near horizontal fractures are completely filled up with secondary materials. In another case, already I have shown, near horizontal fractures, those are tensile associated with the master fault, they are filled up with the pseudotachelite material. But here, these horizontal fractures are filled up with the either siliceous or ferruginous or calcareous material. Now here, the same sample I am showing this one and this one in different angular orientations. One surface, this one, it is showing silicon lines with silicon sides. It is a prominent friction surface. But opposite side, there is no friction. But this surface is coated by the secondary material. So this surface where the silicon lines, it is a compressional surface. At the same time, this surface where the stress released or somehow that is extensional domain where secondary precipitations are happening. But none of them are altered or weathered. There is no signature of any alteration on these friction surfaces. Now, classical example is this one. If you see this surface, it is giving you a shining luster. It is looking like a mirror surface. If this type of silicon sites are exposed on the surface of the earth, so for a long duration, we should not expect this type of shining luster from this surface. Now, photomicrographs from these samples, these are basically representing two different types of brittle deformations or fractures developed within these fault rocks. Here, one type of fault rocks are there. Those are cohesive. Clasps of quartz-feldspathic materials are entrapped within fine recrystallized groundmass of quartz material. These are very cohesive and highly intensely fractured. All types of intra, inter, and transgranular fractures are there within these cohesive rocks, where the narrow zones of Gauss material are very prominent. These type of rocks are generally, we say, cataclasites. Now, within the same rock, within the same cataclasites, there is one type of precipitations following the fractures. These are siliceous precipitations in most cases. In other places, we can see fine Gauss material transecting the fractures within the quartz-feldspathic material. Similarly, in other cases, it is a tapering geometry of a pseudotachylite vein within the gneissic rock. Okay, so these are the microstructural phenomenon of a brutally deformed rocks within this basement material. Now here, this photomicrographs, here you can see different orientations, different sets of transgranular fractures in different orientations, where quartz grains are highly strained. Okay, so we can separate all these transgranular fractures in different sets. All the fractures are completely held up by siliceous or quartz material, and these are part of the cataclasites. Now, following the same fracture, here we can see a calcite vein is there. Ferruginous material is there. Following the same fractures, you have siliceous, calcareous, and ferruginous material. They are injecting following the pre-existing fractures. Now, it is a calcite vein, calcite material, calcite crystal. If deformations are going on continuously, why there is no single intra, or any type of fractures within these calcite crystals from these fractured zones. Now, here, from the same borehole, same basement rocks, if you see this type of photomicrographs, here basically, these are dominated by plagioclase feldspars. Here, interestingly, here if you see, surround these quartz, strained quartz, recrystallized quartz surrounded by feldspars, but feldspars are all sericitized. From my experience, these feldspars are completely sericitized up to 3 kilometer depth level. Not a single feldspar I could find out from pilot borehole also, when I was associated with the BGRL. So all the feldspars throughout this entire zone, from surface, from contact to the drill depth, not a single feldspars remain unaltered. But strain within the quartz and presence of the recrystallization within the quartz, they are representing some sort of strain already it was there within the basement rocks. Sorry? Is it audible? Hello?
Audible, audible.
Yes. Oh,
Yes, audible.
Yeah. Now here, if you see the fractured, brecciated granite basement rock, granite gneiss, where minerals, I'm not going to into detail of the minerals, but this one is the cross polar, this one is the plane polar, where different sets of fractures are there. One set of fracture displaced by another one, but repeatedly they are filled up, injected by the ferruginous and siliceous materials. Same photomicrograph of this cross polar, and this one is representing the plane polar. Now here you can see the presence of the iron, presence of the ferruginous material following the similar fractures within this entire brecciated rock. Basically, these are contributing the color of the basement rock within the fractured zone. Okay, here the same photomicrograph, same section, same material is showing some sort of other typical pattern of these secondary materials along the fractures. Now here, if you see very carefully, this one is representing a crystal of iron and anostomosing fracture network overprinted by another set. They are fully, completely filled up with the iron. This one is the luminescence image of the same thin section. Here, some amount of the secondary precipitations, they are showing different generations, different types of secondary materials, especially iron. They are following the similar fractures. Means fractures are developing continuously, along which secondary precipitations are injecting with time, following the same trend, same fractured zone. Now, how to differentiate this? These two photographs are the luminescence photographs. Here, these are the crystals of the iron. We did EPMA data of this material. Basically, these are hematite. Luminescence image of the same zone material. Here, these are amorphous of the iron. So here we have both crystals of iron, both amorphous of iron. Now, here, point is, secondary precipitations are dominantly iron, then siliceous, and also calcareous. All of them have two phases, crystal and amorphous. Now, timing is a matter of discussion or further investigation. Now, the point is, plagioclase feldspars here are fully sericitized. It may be a pre-existing feature. Presence of cataclasites, they are representing as a cohesive fault rocks, and repeated brittle deformations are there within this basement granitoids. Now, further we investigated the ACM and EDAX analysis. Fault rocks brachia, they have angular clasps entrapped within break-sheeted zone where surrounding materials enriched by ferruginous precipitations. Once set of fractures disposed by another one, they're completely, this dark domain is representing the siliceous precipitation, light one is representing the ferruginous precipitation. At the same time, this pseudotachylite vein is there, material is there, and they are representing almost amorphous material within this fractured zone. Now we did EDAX analysis of this break-sheeted one and also the pseudotachylite one. There we found the class, apart from the class, those are the Gauss or matrix domain. They are showing in a higher proportion of calcium, iron, and obviously there are silica. Okay. In case of pseudotachylite, these are enriched either by aluminum and silica. Okay. Now here, what are the characteristics features of this fractured or fault zone material? There we found in most cases, angular clasps are entrapped within secondary material. Those are mainly either ferruginous or siliceous, and somewhere we have the pseudotachylite material. Interestingly, in some cases, we have nanoparticles of the silica. They are also entrapped within this fine grain fractured material. At places along the friction surfaces especially, there are chloride, where silicon lines and silicon sites are prominent. Now, further, we have done the ACM analysis of these fractured samples. They are representing as a vein where crystals of the hematites are basically following the same trend, where the amorphous material of the iron is also there as a ground mass. Presence of different sets of fractures along with different types of precipitations, they are basically representing in different phases of the secondary materials, either silica or iron. Parallelly, nanoparticles of the quartz are also prominent along the friction surface. Those are basically behaving like a silica gel material along the silicon sites or friction surfaces. Now, pointing to these materials, we did EDAX analysis. Those are basically clearly showing the enrichment of iron and calcium, and CL studies of this one, where these fractures were not visible in the microscope also. Within that, dominantly secondary materials are either calcium or silica. Now, what are the processes to get this precipitation, to precipitate these materials? Or is there any process of cementation? Basically, there, dominantly ferruginous, carbonaceous, and silica are present as secondary material in all cases, in both crystal and amorphous in nature. Dominantly ferruginous, and they are appearing as both precipitation and cementation material. Silica gel or pseudotachylite or cementations are there along the friction surfaces. Calcites or carbonaceous material present as a veins along these fractured rocks. Now, point is, if you have a fractured dimensions, if you can calculate the rate of precipitation versus temperature and the fracture dimension, suppose 10 micrometer wide fracture, it can filled up with this precipitation within 100 years. If rate of precipitation is high, this 10 micrometer wide fracture can be filled up within 1 year. But in our cases, microfractures width basically lower than the 5 micron in most cases. Those are we are observing in ACM or in polarized microscope. Plus, not only the dissolved material is there, some suspended particles are also there that can seal this entire fractured zone within a very short duration. Plus, there is a function of temperature within this seismogenic crust. Now, how it can contribute the rock strength property within this fractured zone or within this basement rock? Here, already we have some publications from BGRL by Goswami et al. It shows from different boreholes, the cohesive strength is basically changing within a range 3 to 35 MPa. Coefficient of friction, it is within 0.7 to 2.7. But if you see the porosity, it is lesser than the 0.4. Now the problem is, whatever the permeability within this fractured zone or the permeable zone, that is related with the fractures. Here, porosity is very nominal in case of a massive rock. Only in case, whatever the permeability you are measuring, that is the fracture within this damaged zone. So that can be correlatable in case of the pilot borehole drilling. In case of caved one, which is 3,000 meter depth, there also it has a strong indication where Young's modulus are very low in case of a fractured zone and high Poisson's ratio within the damaged zone. I think this is up to this, and if you have any question.
Thank you,
Thank you,
Surajit.
Surajit.
Yes, Shandeep, go
For your
ahead.
presentation. Now the session is open for discussion. I think Chirantan has raised his hand. Chirantan, you can go ahead with your query.
Thank you, Shandeep. The Professor Misra, I have two questions. I have like no experience working with core, and I was just wondering. I think one of the slides you showed where the angular relationship between the fracture and the drill core orientation. So I was just wondering, how did you measure the two angle? Because the drill core orientation will be a linear, and the fracture surfaces will be a planar surface. Like, on which plane did you measure, and how did you measure it? Just if you can explain it to me a little bit.
Here, basically, I have measured the angle of the fracture with respect to the borehole axis. Borehole axis, easily we can determine, suppose as for example here. This red line, red arrow is indicating the vertical borehole. All the borehole core samples are near vertical. With respect to that, suppose this is the fractured, with respect to this vertical axis, what should be the angle? This angle we have measured. It is impossible to measure the orientation because these are non-oriented. Okay, so these orientations we have measured for both fractures and fabrics, and that we have plotted with respect to this. This vertical axis is representing the borehole axis, and with respect to this, these are not east-west, north-south. These are basically representing the angular orientation with respect to the near vertical axis.
Okay. And also, I think in slide number 19 or slide number 20, I think you showed a photomicrograph.
Just a minute, Chirantan. I think Surajit,
Yes,
I am interrupting. I think what he has asked, he has a point. I mean, if you are calculating the just the angle between the axis that you have plotted by a red line and the orientation of that particular foliation, then it depends on whether you are actually physically looking at the the maximum deep, or you are looking at a very apparent deep. So the angle will vary. So how do you account for that? I think that was your question.
Yeah. It is. Again, I am explaining. Suppose in case of this fracture, it is a two-dimensional. If you rotate it, just you can penetrate the surface following this trend. Okay. Now I can measure the angle with respect to this vertical axis here, at different points. Where I will get, basically I will measure it, where the inflection point, basically, where I will get the maximum angle of this value. If I consider this point with respect to this with respect to this orientation, basically we cannot measure any orientation of the fabrics. What we can measure at this point, where the maximum angle, deep angle of this surface is with respect to the borehole axis, that we can measure here. Okay, that we have measured.
Yeah, that is correct. If you measure at different points all around the core and then take the maximum, then that will be the best representative direction of amount of deep for that particular
Yes.
That's right.
And just to just to thinking about it, if you have the core axis and if you take a plane, perpendicular to that orientation, and if we measure, I think in that way also, I think we can have a homogenized, a consistent relationship, maybe we'll be able to measure. So my other question to you, Professor Misra, is regarding, what do you think are the sources of those, of the fluid? Because you have, I think in one of the slide, I think slide number 19, you showed a photomicrograph where the vein orientations were very similar, but you have two different types of mineral precipitation. One was, I think, if iron rich, another one was calcite. So I was thinking, are there two different generations of veins, and in general, what are the sources of this fluid? So that's my question to you.
Basically, yeah, that is part of this investigation also. And we have data. We did ICPMS and some EPMA data. Basically, we are expecting it is from the overlying Deccan basalt. Okay. And basically, fluid is carrying from surface towards depth. Okay. We have evidences from isotopic data also, especially oxygen isotope and carbon isotope.
So the rainwater or surface water percolating through, carrying this.
Yeah. And just for your interest, I can show you, it is beyond this discussion. Yeah, here, if you see, this is basically the mass balance we did it. These are basically related with the trace element. These are indicating higher proportion of some elements. Those are not expected from the basement. That is only possible if water percolates from Deccan basalt to the depth.
Okay. Thank you, Professor.
Surajit, there is a question in the chat box.
Yeah. Thank you. Yes.
If you can see, or I can simply read it. Sir, what parameters you have followed for collecting samples?
For collecting samples. Generally, if you see here, first, I have selected the highly fractured zones. Okay. Importantly, here if you see these last two boxes, they are representing the samples from KV6, just in the nearby the location of Koyna earthquake. From my
We are missing you, Surajit. Surajit, are you there?
There is a snap in the connection.
Yeah. Sandeep, can you call him? I think he did not understand.
Sir, I'm calling him right now.
Surajit, it is okay if you can come without slide. Can you hear me, Surajit? Yeah. Surajit, can you hear me?
Is it audible from your side?
Yeah. Surajit?
Sound off.
Just a minute, sir. I have to disconnect. So it is.
Hello. I was speaking from my other system. If you have any query, please.
Yeah, you are talking something, we did not hear you. Can you please repeat it, what you were saying?
Yeah. The question was related with the sampling here. Basically, here what I did, the sampling process, basically I did from selected fractured zones. Those are representing recent earthquake activities. That recent or not, that we have selected based on the parameters of weathering or alteration of these silicon surface or friction surfaces. In case of KV6, the 4 samples we have, there is no alteration, and totally it is basically showing the shining luster without any alteration with only secondary precipitation. Based on that, we have selected these samples.
Surajit, you have accessed, I think, from 2 different instruments. Please
Yeah,
mute one, otherwise there will be echo.
Yeah. Basically, I want to show the samples from different systems. Yeah, these are the samples. These samples is representing a shining luster with a mirror surface. It is a friction surface without any alteration. This type of samples generally I have considered for the study.
Surajit,
Yes, sir.
you have 2 machines on, so you have to shut down one, otherwise there will be echo.
Problem.
That is what Professor Anupam Chattopadhyay has been saying.
Yes, sir. Now, sir, it is one.
No, there is echo. See, in the same room, if you have 2 devices which are open, then you have this problem. You have to close one device.
Yes, sir.
Yeah, now it.
Yeah, now it's fine. Yeah, I think Anupam Chattopadhyay has a question to ask, I think, or
Yes.
queries.
Provided Surajit can hear me properly, I don't know. I had one query, not directly related to the sampling and other things that you have shown. That this is an excellent piece of data, and we have already listened to from Sukanto ji from regarding this earlier, I think, if I am not mistaken. So this is an excellent data, and I'm really enjoying this talk. And thank you for a nice presentation, Surajit. My only question here is that you are showing a lot of horizontal fracture.
Yes, sir. Yes, sir.
From which is nearly perpendicular to your axis of the borehole, the vertical borehole, and we are explaining that these are mostly filled by fluid, secondary material, whatever, different type of things.
Yes,
Both for
yes.
pseudotachylite related fluid, otherwise a normal
Yes.
and silica rich fluid. Now
Yes.
my question is, at what depth you are finding these things approximately?
Sir, for me, because I have project samples up to 1.5 kilometer, that's why I can say up to 1.5 kilometer it is there. But practically it is up to 3 kilometer depth also. I have that information.
So now my question is, for 3 kilometer depth, if you are opening a horizontal fracture, and you have shown to us that these are tensile fractures. So
Yeah.
to have a tensile fracture at 3 kilometer depth,
Yeah.
actually your sigma V needs to be negative.
Yes.
And you need usually a supralithostatic fluid pressure. So is it possible to open a fracture and then infiltrate secondary fluids just into it, or the fluid has to create the fracture? Otherwise, this is very difficult mechanically.
Exactly, sir. You are in the correct point. Problem is that is, sir, in this case, it is we are basically trying to correlate. Not trying. It is evident. Basically, evidences are also there. Just if you can remember, secondary whatever materials are there in both forms, crystal and amorphous. In most cases, what we have noticed, iron, silica, and calcium, those are in amorphous nature. They are commonly present throughout this intersection, either in near vertical or near horizontal. Now, so point is, suppose in case of silica, somewhere some material is there, those are representing the nanoparticles, little bit larger in the crystal size, and they are concentrated on along these friction surfaces, basically behaving like a silica gel material. Okay, now the condition, if it is related with the sudden formation, not pseudotachelite, not the crystal, grain size is very, it can be identified, but it is very nominal. So condition is somehow it is representing a situation where the role of surrounding basically pressure condition is a matter, plus temperature is a matter of formation of this amorphous.
No. My question is not the formation of the surface. You can very much have a very polished surface coated with nanomaterial in a brittle fault zone, which has been shown by a lot of people, right from 2007 Han et al. Paper and others. That is fine. My question is, how do you explain opening of a horizontal tensile fracture related to the deformation within at least up to the depth of 3 kilometers, which usually we have seen this. But problem is everywhere in those cases, like it is very common in many, say, vein type deposits, like in gold fields and others, they are seen. But there is a clear evidence of supralithostatic, very high fluid pressure. But in this case, possibly you have not, either you have not explored that possibility, or you at least don't have right now any major evidence in favor of that.
Sir, I am working on this. I have some evidences. Okay. And basically, we are trying to characterize it from geochemical analysis of the fluid and related with the secondary precipitation.
Okay. Can I interrupt?
Yeah, please.
Dr. Deepjyoti Goswami, are you there? Dr. Deepjyoti Goswami, are you there?
Oh, Deepjyoti Goswami.
I can see him here.
I can see him, but
but he is muted.
Because he could have given some insights from the geophysical log data, and he has worked on the stress as well. Deepjyoti, are you there? I think.
But you can enlighten us, sir. Do you think that the sigma V was extensional by any means in this case?
Sir, should I explain on it?
Yeah. Go ahead.
Basically, sir, what sir was basically was giving me this sort of just here. Basically, these two types of conditions are there in this fault. Now here, this is one side is the representing normal, another is the strike state. This is the condition. But this condition is prevailing up to 2000 meter depth level. Below 2000 meter depth, the condition is basically changing like this. Above 2000 meter depth, the essays, the horizontal max is this one. Okay. We don't have another horizontal means horizontal minimum up to 2000 meter depth level. Below that, somehow we are getting this condition. We don't know it is related with pore fluid pressure or not, but these changes in stress conditions are there at a deeper level.
No, but do you have any idea or any evidence what kind of fault is this? Is it established?
Yeah, it is. I think there is a paper on by Goswami et al. Recently in
No, strike slip and normal. Yeah.
Yeah.
Okay.
Yes. Any further question?
Yeah, anyway, thank you very much. I just wanted to know about the fluid pressure condition because otherwise it is mechanically difficult to explain the extension of stress at that.
And Surajit, there are a few more questions in the chat box.
Yeah, most of the questions are from Sri Hari Prasad Gayatri.
Sri
He's
Hari
asking
Prasad Gayatri,
about,
Surajit, Sri Hari Prasad is sitting with all the students. So
Yeah,
this
yeah,
is
I know.
common questions from everybody.
Yeah. Yes. Basically, these are common problems where we can measure the fracture angle by trying to form a plane using two lines from two sides. Basically, when you are observing on the surface, it is a line, but you have to consider it as a two-dimensional that is penetrating through the core surface. Okay, so from there you need to imagine a point where you can get the maximum deep value of that surface, and there you need to consider the vertical axis by using basically two diagonal scale. You can measure it. One diagonal scale should be parallel with the borehole axis, another should be at parallel with the fractured surface. So how do you interpret the presence of both amorphous as well as ferruginous crystals at the same place? It is there. It is there along the fractured surface. Now, condition how it is that we need to investigate. Okay, there are several depths where we find the presence of very fine layer of secondary material over the silicon sites that can, we say the silicon sites are fresh surfaces. Yeah, presence of very fine layer, that fine layer formed by the process of either precipitation or cementation. Fresh surface means that surface is altered or unaltered. Okay, it is chemically reacted with the fluid or not. In terms of that, I have said the fresh surface. Just that fresh surface, if you keep outside for 1 year, I don't think that will remain fresh as it is. But it is coated by the secondary material, that is as a foreign material. Okay, I think these are okay.
Surajit, are you tired?
Yes.
Are you tired? Yes?
No, sir. No.
Okay, no.
I'm
So
okay.
can I
I'm
have
fine.
some query? I have some query.
Yes.
So you said that the master fault is vertical, right?
Yeah. Sir, in this case, with respect to the borehole core sample,
Yeah.
the branching or other fractures that is generating from another fracture. The fracture is the responsible for that secondary fracture. That is here I am seeing as a master fracture. But that master fracture they can have another master fracture if you consider the fault zone. So master fracture is basically related with the another set of fracture which is responsible for their development.
Okay. So do you have any idea what could be the orientation of this fault zone? That should be vertical, right?
Sir, it should
Because you said it is sigma 2 is vertical, and you said
Yeah.
this is a strike slip fault. That has to be vertical, right?
Yeah. So the features we have noticed from surface, and it is continuing up to the depth of around 1.5 kilometer, and it is continuously, means it is continuing from basalt surface up to the drill depth for this type of borehole samples. But it is difficult to continue as a straight near vertical orientation up to a deeper level, suppose up to 6 or 8 kilometer depth. It is basically a anastomosing fracture network. It is continuing from the fissure zone up to the hypocentral depth. Okay, sir. So the zone dimension, it is another problem. I think that need to be that need to define very precisely.
My last query. Do
Yes.
you have any estimation of temperature that this falls on?
Yeah. I have. So there are 2 points. 2 points means, suppose if friction surface is there, that will generate one. There is an equation. Suppose H is equal to 2 tau U. If you have one friction surface, the temperature will generate. If you have a pulverized zone, their temperature can generate up to 100 degrees centigrade temperature. It can increase. One. Now, here if we follow the normal geothermal gradient, temperature should not
No.
exceed 180 degrees centigrade. Okay, sir.
180.
Now, yeah, because of the present geothermal gradient here, approximate up to 200 we can go. But the flow of the silicon nanoparticles or formation of these, at least we need 250 to 300 degrees centigrade. But we have a chloride thermometry that indicates around 250 to 300 degrees centigrade temperature on the friction surface.
Okay.
Yes, sir.
Okay. Thank you, sir.
Shureta, may I ask you something?
Sure.
Shureta, I have very basic question. How do you distinguish tectonic fractures and fractures related to the borehole drilling? Because at the time of drilling, it will generate few fractures on the rock, right?
Yeah, you are talking about natural fracture and artificial fracture.
Yes.
Yeah. So if it is artificial fracture, you will not get secondary precipitation. If it is natural fracture, you will get secondary precipitation or alteration or filling of the fractures.
Okay. But you have shown slicken lines. Slicken lines can also form this drill holes, right?
No. This type of it is not possible. Silicon lines cannot form because the rotation of the drill hole and the orientation of the fractures and silicon lines, they are in different orientation. Plus, if you rotate a brittle hard rock or the material will fracture, there will be no friction at all on the surface.
Okay. And another question is, you have already mentioned that the maximum temperature of the fault zone was nearly about 300 degrees centigrade, right?
No. In a fault zone temperature, no, it is real. If you are talking related with the frictional temperature or fault zone temperature.
Frictional temperature.
So no, that can be more than this, because you are generating the pseudotachylite.
Okay.
So there it can be more than this 300.
Okay. Thank you, Surajit.
Okay, thank you.
I think Chirantan has another query.
Yeah, I think Professor Ray is also there and raised his hand for some time, before me at least. So, Sumit
Ray.
Kumar.
Sumit, yes.
Yes.
Yes, please go ahead.
Yes, I had, first of all, I must thank Professor Misra for an interesting presentation. But I had a query. You had drilled through the Deccan Trap to reach the basement rock, isn't Professor Misra?
Yes.
So what is the age of this brittle deformation, particularly development of the pseudotachylites? Are they pre-Deccan Trap placement or post?
That we have not studied. Okay.
Because
The presence of these fractures or pseudodactylites associated with the other fractures, they are in the same place, in same domain. Okay, sir.
yes, I understand that there are cataclystically deformed rocks as well as pseudodactylites, frictional
Yes,
heat generation, and
Yes.
melting. All these features are there.
Yes.
Now, if these may be before the emplacement, before the Deccan Traps were
Sir, one thing it is clear: cataclysite cannot form in present situation. Definitely, cataclysites were there before reactivation.
Before
reactivation or ongoing seismicity, cataclysites were already there.
Cataclysites were already there.
Already there.
So
At this
you mean
scenario, cataclysite cannot form. It is not possible.
cataclysites, if those were already there before the Deccan Trap emplacement, so how these are significant for the Koyna or the other Varna earthquakes? Which are much later. Another question I will ask. Another question comes to my mind. Did you get similar features in the overlying Deccan Trap? That means pseudotachylite or evidence of brittle deformation in the overlying Deccan Trap?
So brittle deformation evidences are there. Like Gauhati, Koyna fissure zone, it is there, and it is continuing from surface towards depth. Brittle deformations are there, but cataclysites are not there, and it is not expected within Deccan.
Forget about cataclysites. What about pseudotachylites?
Pseudotachylites are not there. I did not see any pseudotachylite.
Because in 1913 or 14, when the project was just at the initial stages, the drilling was through the Deccan Trap only. Then I had a brief chance of examining these boreholes and borehole cores, and I found at one places there are some vein-like things which look like pseudotachylites. I wanted to have a specimen, like at least 2 or 3 centimeter long core, but at that time probably it was not. There was the courts were not to be given to outsiders, so that's why I couldn't. That curiosity that remained with me, but I think that may be examined. That overlying Deccan Traps, whether those pseudotachylites or evidences of brittle deformation are present or not, because otherwise the seismicity of that area cannot be linked. This what you have described, these are essentially within the basement rocks. So those may be much before, those may be Proterozoic or older features. So they may not be in any way linked to the Koyna or Varna earthquakes, which are recent events, or maybe reactivation of some recent events. But otherwise, the establishment of the link may be very difficult.
Okay. No, there at least we can correlate with the rate of alteration of this fractured rock or fault surfaces with time, and also can, if possible, we can correlate with the presence of precipitated materials.
So that would rather go because if it is before pre-Deccan Trap emplacement, so these were very close to the surface, isn't to the at that time Earth's surface. So near surface, the fluid activity or percolations or these things are rather possible than 1.5 kilometer below, which is its present location, isn't? So the fluid activity or the alterations, and particularly the gouge formation, because gouge formations is a near surface feature. Say within a kilometer or less than that, gouge in seismic slips or even in a fault zones, gouge is unconsolidated rock forms only in near surface features. So I have a doubt that these, what we are observing, may be very old features, pre-Deccan Trap emplacement. What is your take on this?
So I think this incohesive fractured material, whatever we are getting around within 1 kilometer, 1.5 kilometer depth, they are very much fragile and they are incohesive, and it can be loose at any cost. Now, this type of material, I think we can expect up to 3 to 4 kilometer depth. Below that, that can be more cohesive, more compact. Okay, sir. Up to 3 to 4, we can expect some sort of this fractured or highly brecciated material.
Fracture is okay. Then I had some doubt about the gouge material. Gouge is unconsolidated rock. Okay. If you think that it can form up to a depth of 3-4 kilometers.
Yes.
Okay. That's all. Thank you very much, and thanks for the nice presentation.
Thank you, sir. Thank you.
I have a very small question to you, Professor. So I think you mentioned somewhere during the presentation that the veins that you were observing, they are tensile. So I was just wondering, how did you determine that, as tensile, not extension?
Yeah.
Like sigma 3 to be negative.
Yeah. Just I have to go there. Suppose in this case, okay, can you see the last two ports?
Yes.
These two ports. Okay. Suppose this one. Okay. So you have a cylindrical core sample without any fracture for this case. Okay. Without fracture, it is a cylindrical core. Now you have to create these two sets of fracture by creating a load from two endpoints. Suppose UCS you are doing. So there can you expect a range of 60 to 70 degree angle of conjugate fractures in this case. Now one side, this surface is representing slicken lines with slicken sides. At the same time, in other side you don't have. This is a very common feature throughout this interval. And here you don't have any slicken lines or friction surfaces, but there you have the secondary precipitations. So if I create, suppose sigma 1 is near vertical, one surface I am creating the friction, another surface, it is in the direction of the extension. It is related with the tensile cracks. So this type of feature, it is from KBH 7, I can remember. So this type of common features are there throughout all the boreholes. Yes, sir.
Okay.
Yes.
Thank you.
Yes. Any further questions?
Shantanu sir, I think there are no more queries.
Yeah. We must congratulate Surajit, because he has really responded to us in a very short notice. We thank Surajit for this.
Thank you, sir.
And Surajit really deserves a big round of applause for an excellent talk. And I hope Surajit should join every month to us.
Thank you, sir.
And with this note, if our Shayandeep has anything to announce or declare, you can. The mic is over to Shayandeep to close the session.
Yeah, thank you, sir. So from next month again, Dr. Jyotirmoy Mallik will be hosting the monthly lecture. So thank Surajit Da for presenting his talk with actually in a very short notice. So I'll now like, to the permission of the chair, I'd like to end the session, and thank you all for attending this monthly lecture session.
Thank you, Shayandeep.
Thank you.
Thank you, Shandeep.
Thank you, Shayandeep. Thank you very much.
Thank you, sir. Thank you.
For arranging.
Thank you, Surajit, also.
Short notice. Okay.
Yeah.